Hi, in this lecture we are going to cover Chapter 8, Alkenes, Reactions and Synthesis. In this chapter we are going to see reactions and synthesis of alkenes. So, when you have alkenes, we can obtain a variety of other functional groups through some reactions. And these reactions are very common in organic synthesis. So in this chapter we are going to cover these topics. First, we are going to see how we can prepare alkenes through elimination reactions. Then we will go to addition reactions, halogenation of alkenes, addition of Cl2 or Br2. Then we are going to see halohydrine formation from alkenes, addition of HOX. Then we are going to see hydration of alkenes, how can we add water to alkenes. Then the last we are going to see addition of water by hydroboration. The difference between 8,4 and 8,5, this is oxymercuration reaction. The second one is hydroboration reaction. Both produces addition of water to alkenes. Let's start. The chemistry of alkenes dominated by addition reactions. So if you have a carbon-carbon double bond functionality, you can add XY and we are going to form an addition product to carbon-carbon double bond. And the reverse reaction is called elimination reaction. We can eliminate X and Y and we generate an alkene and XY. So let's see the specific examples for elimination reactions. When you have an alkyl halide, a halogen connected to an alkane, we can eliminate halogen and a hydrogen from a neighboring carbon through some reagents, and we obtain alkenes. This reaction is called dehydrohalogenation. Dehydrohalogenation occurs when you use a strong base like potassium hydroxide, but at this moment you don't have to know any detail. The second elimination reaction that we are going to see is dehydration reaction. As you remember, dehydration is loss of water. In specific, if you have an alcohol which is an ROH functionality, here we have an hydroxy functionality. So when you have a hydroxy functionality, so what you can have, you can lose here a hydroxide and a neighboring hydrogen, one of them. In this case we are losing a hydrogen from this carbon. Let me just here write that one. Let me show you this one here. And when you lose OH and H, so we are introducing here a carbon-carbon double bond. So this is also called an elimination reaction, but specifically its name is dehydration. So when you see these kinds of reactions, what we have to understand, the upper reagents here are catalysts and reagents that react with this molecule. The lower one, THF, is here a solvent. Most of the organic reactions occur in solvents, and also here you see the temperature. So the green ones are the reagent and the black ones here are solvent and the temperature. But in future we are going to see more. Let's see a specific example. This is an example from your book. It says that how many alkene products we can generate using this alcohol and if through a hydration reaction. So basically it asks how many alkenes including E and Z isomers we can obtain from this alcohol. So let's do this. Generally I use skeletal drawing for this type of questions. Let's see. So we have here 1, 2, 3, 4, 5, 6. Let's count here 1, 2, 3, 4, 5, 6 carbon, and here we have 1, 2, 3. At the third carbon we have an OH, and as also at the third carbon we have a CH3 group. Okay, so the rule for dehydration reaction, you have to lose here the hydroxy group on the carbon, and on the next carbon, on one of the next carbon, basically you have to lose a hydrogen, and you have to generate or produce a carbon-carbon double bond. So let's write hydrogens on the neighboring adjacent carbons. It has to be immediate one. So we have here another carbon having hydrogens, neighboring one. So here we have 3 hydrogens. I'm specifically showing the hydrogens. So basically we are going to lose this hydroxy group, and one of the possible or one of the candidate on the neighboring carbons we are going to lose, and we are going to generate carbon-carbon double bond functionality. Let's keep moving. So let's say that we are going to generate, let's say we are going to lose this position, I'm going to call A position, this carbon. If we lose a hydrogen from this carbon and hydroxide from this carbon, the carbon-carbon double bond will be here. So let's just draw the structure 1, 2, 3, 4, 5, 6, and double bond will be here, right? So let's specify here. That's the double bond. Can we have E or Z isomer? Okay, let's see. I'm going to look at how many substituent around double bond, and also let's not forget there is a methyl group here, a methyl group. Yes, then I'm going to use red color to identify the carbons, carbon-carbon double bond. So we have here, and I'm just chopping this bond into 2 halves. Here on this carbon, let's say this is number 1, this is number 2 carbon. On this carbon we have here this alkyl group and hydrogen, and on this carbon we have here a methyl group and here an ethyl group. You remember, for the designation of E or Z, higher priority groups around double bond has to be on the opposite sides when it is E, and they have to be on the same side for E isomer, Z isomer, sorry. So let's decide hydrogen versus 1, 2, 3. This is a propyl, right? So let's say this is propyl, this is ethyl, and this is methyl substituent. Let's decide which groups have high priority. Ethyl versus methyl. Ethyl has high priority, so higher, and this is lower priority on this side. What about this side? Propyl has higher priority, hydrogen has lower priority. So higher and higher priorities for this particular alkene, they are on the opposite side, so this is going to be an E isomer. So I'm going to say this is E isomer. E isomer. Can we get Z isomer? Yes. So instead of this, let's draw for the plus. So how can you generate the other isomer from E? How can we get Z isomer? Just change methyl to like methyl versus ethyl, you can generate Z isomer. So I'm drawing the same. So 1, 2, 3, 4. There is a double bond here. So methyl, I'm going to draw up, this one here, and ethyl I'm drawing this way. So basically, if we lose hydrogen from A, so these are A. So how about let's go to B position, this position. If we lose hydrogen from here and hydroxide here, we are going to introduce double bond here, so that's going to be another product. So let's say these are A, and for B I'm going to draw here the B's. So I'm just going to draw double bond here. So 1, 2, 3, 4, 5, 6. So double bond will be here, and there is a methyl group, right? CH3. I'm drawing without CH3 here. It's like a pure skeletal structure. So we can get this one. Also, let's check, can we get E or Z isomer from this specific alkene product? I think yes. So if we just look at here, we have here a methyl, and I think there is 4 carbon butyl, so this is high priority. And if you look at, so let's say low and high, and here there is a hydrogen right here, so let's say high. I don't want to confuse this hydrogen with high, so this is low. So this is CH3 versus hydrogen, so this is higher and this is lower priority. High, high, they are on the opposite side, so this alkene is E. Okay, then let's draw the Z version of this one. I'm going to use the black color again here. So again, how can we do it? You can do in 2 ways. You can exchange these 2 groups here or these 2 groups. I think it's easier to change this one, but you can do also the other one. But I'm going to change this methyl with hydrogen. So again, I'm drawing 1, 2, 3, 4, 5. There is a double bond. Hydrogen will be down. We don't show hydrogen, right? So methyl group will be up. So this is the Z isomer. So I'm going to put here in parentheses. How about the product C? What is the product C? Let's say this is the C position, this carbon, because it's also next to this hydroxy group, right? So if we lose a hydrogen from here, double bond will be introduced here. Let's draw that one. So 1, 2, 3, 4, 5, 6. There is a methyl, but methyl losing 1 hydrogen, and double bond has to be here. So OH lost, hydrogen lost. Can we have E or Z isomer here? Let's see. Do we have 2 hydrogens here? The third one lost. The rule says that when you have 2 same groups on 1 carbon on the double bond, you cannot have EZ or cis trans. So that's only one possible product, elimination product. So in total, we have, if we lose hydrogen from this position, we can have E, and we can have here the Z product, Z isomer. In the second case, we lost hydrogen from this carbon, specific carbon, and this OH, so double bond will be introduced here. So we can have this E isomer, and this is the Z isomer. And if we lose a hydrogen from this carbon, which is next to the carbon bearing the hydroxy group, so double bond will be here. We showed here we cannot have E or Z isomer specifically for this alkene. Okay, this is a good example to see how elimination can occur. The second reaction is halogenation of alkenes. Addition of X to X here, halogen, can be ClBr in this specific case. Okay, bromine and chlorine can add rapidly to alkenes, and we generate 1,2 dihalides, and the process is called halogenation. And the reaction is this: you have a carbon-carbon double bond functionality and alkene, you have a halogen, a diatomic halogen molecule, and this will be added to double bond. So Cl2, Cl will be added to each carbon, and these are called 1,2 dihalides. And in this specific case, we have an ethylene and Cl2. We are obtaining 1,2 dichloroethane. And let's continue. How the reaction can happen? Basically, you remember the reaction mechanism for addition of acids, HCl or HBr. First, double bond attacks H. If it is an HCl, then Br leaves. We form a carbocation, and then the anion, bromide, or sometimes it's chloride, attaches itself to the carbocation. This is a possible mechanism. Is this a real mechanism? We are going to see that this mechanism does not occur in addition of halogens. So halogens, they don't follow this reaction mechanism. Instead of that, we have a different mechanism. What's the mechanism? Basically, when you have an alkene and a halogen molecule, first we form a cyclic intermediate. If you have bromine, we form a bromonium ion. So what is the reaction mechanism? I'm going to here like draw a little bit detailedly. So when you have a carbon-carbon double bond, and when you have, let's say, Br and Br, the reaction occurs in two steps. The addition of Brs to each, in this case Cl, in this case is Br. So the reaction occurs in these two steps. In the first step, alkene acts as a nucleophile and attacks one of the bromine atom, and what happens? This bromine leaves. But at the same time, one of the lone pair on bromine attaches itself to the second carbon. So one carbon is attaching itself this bromine, and at the same time this bromine attaches itself to the other carbon on the double bond. We form, and here I'm going to draw here, we are forming a cyclic structure like a cyclopropane if this is a carbon. So this is the intermediate, and it's called bromonium ion. This is positively charged. It has two lone pairs. Okay, so this is the first step in the formation of halides. And in the second step, which we will see, the bromide anion that left attacks one of the carbon here, and this other carbon bromine bonds break, and we form this dihalide, bromo. So that's the reaction mechanism. How this is basically proved? When you have an open alkene, when you can have like cis or trans possible, because carbon-carbon single bond can rotate, right? But when you have a cyclic alkene, there are two possibilities. You can have a trans product, the BBr, because like when you have here this sigma bond can rotate, right? If you form a trans at the beginning, it can turn and it can form a cis product, or if you form a cis product, it can rotate and you can form a trans product, because the carbocation we form, if we assume that this reaction mechanism is correct, it's planar, and the attack from top side and attack from the bottom side is possible. So we need to get both cis or trans product. But if it is an open alkene, the carbon-carbon sigma bonds can rotate freely. It doesn't matter whether you form a cis or trans. It will come to the lowest lowest energy conformer. But when you have a cycloalkene, the result is this: we don't see the cis product. So cis product does not form, only trans product formed. So this reaction produces anti-stereochemistry. What is anti-stereochemistry? Bromine and bromine anti to each other, 180 degree. If you look from here, the dihedral angle. So it's trans product is the only product. How can we explain the trans product? Basically, the reaction does not follow this mechanism. If it follows this mechanism, we have a flat planar carbocation from top and from bottom. 50-50 statistically, we need to get this product and that product, but we are only getting trans product. If we are getting trans product, the reaction mechanism should follow something like this. I'm going to explain in the next slide more. So Here, for cyclopentene, again, we can look at the reaction mechanism. The reaction happens in two steps, as we said. This is a proposed reaction mechanism. Later, the scientists they obtain some evidence that the reaction actually occurs through this intermediate. Okay, so in the first step, again, like one of the double bond electrons move to bromine, and then one lone pair move to other carbon, and we form cyclic bromonium ion, cation, and the second bromine can only attack from the top side because the bottom side is occupied. That's the reason why we get the trans product. Okay, I'm going to show a couple of models, and you will be able to see better. So this is the first one. This is the ethene, and when we obtain the cyclic bromonium, and in this case, yes, this is bromine, cyclic bromonium intermediate, the second bromine can attack from the opposite side of the bromine atom on the ring. So it can come from here, and this will open. That's the reason why we obtain the trans product. And the second model is basically this is a cyclopentene bromonium cation. As you see, again, like the second bromine will attack from this from the bottom side, and we will get the trans product. And the third model I will show you actually is the simulation of reaction. Let's look at. You see here cyclopentene, and here I prepared with the chlorine, but you can say these are bromine, you can assume. So how the reaction happens, how Br2 or Cl2 adds to double bond in this particular reaction. And you remember, let's go slowly. First we form the cyclic chloronium, let's say in this case cyclic chloronium intermediate. And what happens, so you don't see the bonds here, but you can imagine that there is a carbon chlorine bonds. In the second step, this chlorine has to go opposite side and attack because this side is occupied. I'm going to show that animation also. Yes, so you see there is the cyclic, so you can assume again here the bonds. This is cyclic chloronium ion, and the second chlorine will attack from bottom side, and you see it's coming. This bond is breaking and this bond is forming. We obtain the trans product. Chlorine atoms, they are added to opposites from opposite sides. So basically this is a stereoselective reaction. What does it mean? Only we form one stereoisomer, not the other one. We didn't form the cis, we form the trans product. Okay, let's move to the next topic, which is halohydrin from alkene from addition of HOX, which I will explain in the next video.